Alrighty, this is a recap. Static friction versus kinetic friction. Kinetic friction literally means in what? Kinetic, what do you think of? Moving, so in motion. Static means not moving. In stasis is what I think of, like cryostasis or homeostasis or stagnant. Sure. Not moving. All right. So those are what I think of. Typically, just like my moving the couch example, which one's typically higher? The available static friction or kinetic friction? I heard two different answers. Is it harder to move the couch or get the couch moving? Get the couch moving. So that would mean static is bigger if you're struggling. What I think of is that phone game like Dune, or like there's one with a bird and it jumps up the hills. You know what I mean? Dune. Is that relative? And what it really means is as you are still, you're locked into place, but when you're moving, you're actually gliding along those hills, and actually the more hills you skip and glide over across the top of, the less you settle, the faster you're moving, and then the I think the bird zooms out, or whatever you're jumping with zooms out. Is that true? Am I making that up? Some of you are like, I know this game. That makes total sense, Mr. Kwan. Kinetic friction is way less the faster you're moving, and I think it dips off. Here's a graph just in case if you don't understand the game. This is the applied force in Newton. So as we increase the applied force, as we move across this way, our available friction gets used up, and we get to use more and more of that friction to do what? What are we trying to do if this is before it starts moving, right? Yeah. So what's friction doing? It's if this is the force to try to get it to moving and we're too gentle, it's not going to move. So this static force does what? Keeps it from moving, right? Yeah. Okay, so it's not moving. It's balancing out the push. The force left is equal to the force right, and then all of a sudden right here, it breaks down. And now we start to use kinetic friction. Okay? But the topic that we're talking about today is actually statics. So we're going to talk about a problem set where it is not moving, and this is not the full-on statics. We have more in depth later. But if it's not moving, it's kind of nice because everything. So for something to not move, if the net force equals 0 ma, that acceleration must be 0, right? Not moving. So our net force is 0. If that acceleration is 0, our net force is 0, yeah? All right. Let's get to the sample problem. A flat rock with a mass of 20 kilograms on a rough horizontal plane. If the coefficient of friction is 0.22, find the least force required to move the rock. If the force acts horizontally in part A, and then at an angle for part B and C. So let's look at just horizontally in part A. What forces am I worried about drawing?
The horizontal force applied to the box.
So we've got a force applied. What fights the force applied to keep it from moving?
Friction.
And that friction comes from mu times force normal. And what's going down? The weight, yes. Force gravity or the weight.
I meant like actually weight. I was confused.
Homophones are a powerful thing. Force due to gravity in this case. because your acceleration is 0, your force due to gravity minus force normal equals the net force. But that net force is 0, right? So if it's equal to 0, we can say Fg equals force normal, right? Mg equals force normal. And so force normal equals 20 times 9.8, right? Are you good with that? Wait. That's just side to side. I'm not going to close that box because that's not our answer. What else? What happens in the side to side direction? The net force in the x direction, if this is the y, what happens in the x direction? Yeah, we look at our picture, force applied minus force friction. Force applied minus force friction. And our applied force, we also know that this is also equal to 0, right? And so we can say that our force friction equals our force applied. What's our friction equal to? Mu times force normal. And our force normal is 196. So 0.22 times 196 is how we apply our force. That's it. What do we get as our answer? I agree. 43.12 newtons. That's our applied force. That is if the force is going horizontally. Okay? Now we're going to change the angle to 37 degrees. Good. Gravity stays the same. I think that's the only thing that actually stays the same value. Why? What else happens? What offsets gravity? Force normal. I'm going to draw it a little short. Because in this case, we are pulling at an angle. What's that angle? Okay, let me see if I can sneak that in there. 37 degrees. And we don't know how hard we're pulling either, do we? We don't know how hard we're pulling, but we do know that we have two upwards forces, right? And then we have two side-to-side forces. We have one downward force, but what's opposing all this motion? Friction. So that holds us back. Opposite direction, yeah, of the force applied. So we've got the force friction, we've got force gravity. We need to make sure we label these. A lot of times our diagrams are labeled. It's draw and label. What's up? And then this is the force applied. Alrighty. Alrighty, we had a break for attendance. What's going on? So we've got our diagram here. We've got gravity going down. We could figure out that that's 196 again, right? That hasn't changed. But our normal is less. We can't figure out our applied or our friction because we don't have a normal yet. And we can't find our applied because that's related to how hard we need to push based on friction. So we've got a lot depending on each other, right? And so what do we know? Do we know that it's moving or not moving? All right. So the least we can do if it's not moving is at least we could set up our equation. And so I'm going to set up our equation for our force in the y direction first. Because that's where we started last time, right? The y direction. And so for my notes to be the same, the force in the y direction is what and what and what. Now there's three whats. Right. Which way do you want to be? Positive. I don't care. because it equals 0, right? So if you say that gravity is positive, it's gravity is positive, and then we're going to subtract off the force normal, and we're going to subtract off force applied in the y direction. The reason why I don't care is because what is this all equal to? 0, which means I could move the negative things to the other side if I need to. Here's the crazy thing, though. I don't want to move everything. I think I'm gonna only move over the normal force. And that's unintuitive, and that's because I've practiced this a lot. But let me tell you that I'm going to say that we've got the force of gravity minus the force applied sine theta, right? That's the y direction, equals the force normal. The reason why I picked force normal to separate is because what's dependent on the normal force? Friction. And that's an x and y issue, right? Wait, that's an x issue, not a y issue. Okay, so then let's figure out what's the same idea, but we're going to do the force in the x direction, which is also equal to 0, right? I'm going to put the equal 0 first. What's opposed in this case? Friction and force applied. So we know that it equals 0. So force friction minus force applied cosine theta is on that side. So in other words, I could say that the force applied cosine theta equals force friction. Is that force applied this force applied? The force applied is this diagonal. And so when I break it down into its parts, yes, they're related to each other. They are identical. No, it's not this force applied. The only thing that was the same is gravity, because everything else is dependent on each other. Fa cosine theta. What did we say friction is always equal to? Uh-oh. Do you see it now? This force normal that you just wrote right here, we can plug this all in for. That whole thing. So, to plug it in, I have Fa cosine theta equals mu. And instead of writing force normal, I could say Fg minus Fa sine theta, because that is force normal. We need to get force applied onto one side, and it's inside the parentheses and also on both sides. So first thing I need to do is probably deal with the parentheses. So distribute. I'm going to run out of space if I don't move it over here. I'm going to say Fa cosine theta equals mu Fg minus mu Fa sine theta. No parentheses anymore. We still need to get this to the other side. It's being subtracted, so what do we do to both sides? We can add it to both sides. So I can say Fa cosine theta plus mu Fa sine theta equals mu Fg. How do I get Fa by itself? It's on two parts of this now. Factor it out. So I'm going to say Fa, and then I'm going to open up a parentheses and say cosine theta plus mu sine theta equals mu FG. Let's close our parentheses there. How do I get FA by itself? After we factor it, we need to divide both sides by that term. So FA by itself equals mu FG divided by cosine theta plus mu sine theta. Can I find what mu is? Is it a number? 0.22. We used it last time. FG. Did we solve for it already?
Yeah.
196? Cosine theta. Do we have the angle? What's the angle? 37. Plus mu, that's 0.22, sine 37 again. We have all the numbers. We can type it into the calculator, solve, and we get slightly bigger of a force than 43 because some of it is used to do the lifting. It doesn't change much. It feels almost the same pull. It might be more convenient for you to pull it at an angle, just like pulling a wagon handle up at an angle. Doesn't always give us an advantage, but sometimes it does. Sometimes it makes the box and items lighter. But when you really want to dig your heels into it, you pull level sometimes. Just depends on what your friction is. Wait! I'm out of space. How am I going to set this whole thing up for part C again?
You just invert the angle.
Yeah, you just changed the angle. We solved it for both part B and C. We have a big, long equation, but all we have to change now in our calculator is throw in a negative sign in front of those two angles. Instead of having positive 37, you have negative 37 as your angle. So the points for something like this would be distributed across all the work for part B and part C, right? So if this was a 10-point problem, 10-point problem, 10-point problem, this would be 10 points. But this work right here, I'd probably divide up the points out of 20 points, right? Doesn't that make sense? So it feels like it's taking longer, but at least I'll give you more points for having it done. Okay? I don't know if that makes you feel better because now all that work is worth more. But at the same time, at least you're getting points for getting through it or trying to. Okay? Yeah, I don't know how much I like that problem either. But guys, what is your answer dependent on now? What's on this side? So we've got gravity. That's easy. mg, right?
Yeah.
Mu is one of the dependencies, and then the other one is the angle. And that's all you need to be able to plug into this equation at this point. So I could say, okay, now we're on a different surface.
Well, the coefficient just changes.
The coefficient changes, but nothing else in terms of the equation. Oh, we're at a different angle. Change the angle then. Oh, we're going to use a different box. Change that box. We've already solved for the equation. Okay? So that's why it's convenient for us to use the variables when we're rearranging like this. Okay? Let's see it even deeper. All right. We've got a box set on a ramp. This is a cool problem. Sample 2. We're looking for a critical angle. And for, oh, by the way, the first answer to this one was 45-ish. 46-ish.
I got 46.3.
46.3 sounds like what's on my key. And then the other one's like 65-ish if you change your angle to negative. Okay? So, which makes sense because now we're pushing it into the ground. We get more friction, and we don't get as much force moving forward. We have it moving down, right? And so it increases both cases. All right. Let's look at number 2. We're looking for a critical angle, which is the angle just before it slips. And critical angle is going to be a phrase used regularly. And so we're using theta c to find the critical angle. And that happens to be this angle right here. And they labeled it way out here, bridging these two lines. But you're used to seeing it right there, maybe. Theta. And we have how many real forces acting on this box? Let's start drawing. Give me real forces. Okay, so we've got gravity, mg. what other real forces do we have on this box? Yeah, that's the whole idea behind this unit. We're going to have friction. And the friction will hold us up while it wants to slide down because it's at rest. And then we have, wait, what else do you have? I heard somebody else say the right answer. I just was busy with the friction because that's what people said first. We've got the normal force out here. And the force normal should be long enough to bring us back on track onto the ramp, right? Because force normal, here's me redrawing force normal right here. The addition between gravity and normal. Why did I draw this a dashed line? It's a vector that I already redrew, that I'm just redrawing. So it doesn't really exist right there. That's true. And then this is a different color and dashed lines because that's also a vector that doesn't exist. What is this? Okay. So force normal is always what? Or almost always what? Equal to gravity what? On cosine theta. And then this, down the face of the ramp, what did we say the other day? That this red one is mg sine theta. And that's the force of gravity down the face of the ramp. Okay, I just nicknamed it FGX because if we turn our paper, it's the side to side. Right? If I turn my paper like that. Why would you do that? It's already on this side. Mg sine theta.
I know, I was gonna say.
All right. So what is the critical angle? What versus what is really going on here for it to not move? So again, the net force is equal to ma. The a is 0. So the net force is 0. So what are we able to say?
Acceleration. Or F9 is equal to
Equals what versus what?
Force down the ramp.
Force down the ramp minus friction. What's friction? Mu force normal or mu mg cosine theta. Well, we're not moving, right? So if we're not moving, can I move one of those to the other side? They're balanced. Mu mg cosine theta. I moved that to the other side equals mg sine theta. What's the same? I was going to say force. You're not wrong. You're not wrong. Mass is the same, but also gravity is the same. Yeah, gravity. And so m and g are both on both sides. So the force of gravity doesn't matter. I've got mu equals sine theta over cosine theta, which is a trig property, a trig identity. Does anybody have it memorized what the trig identity for sine over cosine is? Tangent. If you don't know where we got this, because some people are not in pre-cal, it's been a while since geometry. Some people are past pre-cal. It's been a while. Remember that sine is equal to what over what? Sine theta is equal to equals opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. We're going to take sine divided by cosine. So that's opposite over hypotenuse divided by adjacent over hypotenuse. And what cancels out? The h's. So it's opposite over adjacent. And we know that opposite over adjacent is also equal to tangent theta.
So, I said slope. I knew what I was saying.
you did say slope, and you're not wrong. So this is the slope, and slope is also tangent theta. Mu equals tangent theta. Our mu value we know, so why don't we just do the arctan? Is that arctan? Arctan of mu gives me my theta. Did I forget something? Is there a mu still somewhere? No, that's it. Is that it? Everything else canceled out? So again, you could imagine some multiple choice not giving you the mass, and then you getting stumped. It's like, what do I do? You could figure out like, hey, you might have to write a phrase about why mass cancels out in a free response. Things like that.